For the second part of our review material today, we want to keep talking about the information that's contained in a scientific measurement, and we want to specifically look at now significant figures, and we're also going to quickly review dimensional analysis. So in the previous review module, we talked about the different pieces of information available when you report a scientific measurement, and how scientific measurements are typically reported as the average measurement, plus or minus an error or an uncertainty, and then the average as well as the error and the uncertainty are reported with units, which allows you to scale and compare to other measurements. It's important to recognize that when you report any measurement in any scientific field, the number of digits that you include in the measurement also is an essential piece of information. And the convention in science is the more digits you include either in the average concentration or the standard deviation of our concentration in the case we're showing here, indicates that you have greater confidence in your accuracy in the measurement that you've made than if you report fewer digits. This is a concept you've been exposed to before, but may have not discussed it quite in these terms. This is the idea of significant figures. So in our review module here, we are going to quickly review the rules for identifying significant figures in a measurement, talk a little bit about what significant figures imply. We're going to give you some reminders when you're working a word problem in class, how you decide how many significant figures to carry in your answer. And then lastly, we're going to quickly review dimensional analysis as kind of a general approach to solving problems. So in terms of the reading that goes along with this module, you should have read Harris Chapter 1, Section 1, and that will pretty much take you through all the way through the lecture material here. In terms of vocab, you want to review the concept of accuracy and precision. You want to go back through the fundamental and the derived SI units that we presented in the last module, most likely, and then recall to yourself or come back up with your working definition of what significant figures are. I'll give you my definition, Harris's definition, but make sure that you can walk away from the end of this lecture defining significant figures for yourself and particularly articulate why they're necessary when you report a scientific measurement. First, I want to give you a little bit of kind of a reminder of the context for why significant figures are particularly important in scientific measurement. And for our example, we're going to go back to the example we alluded to in the previous module, where we talked about using scanning tunneling microscopy to measure the actual diameter of a benzene molecule. And the reason your instructors and your professors and your TAs and the people you've interacted with in science classes and science labs in particular in the past have really likely harped on significant figures is significant figures are fundamentally, scientifically, and essentially legally a statement of how accurate or confident you are in the number that you've measured in an experiment. And so you need to recognize that when you report the result of an experiment, the more significant figures you include in your measurement, the greater the accuracy that you are claiming. And in some scientific experiments, particularly in an analytical chemistry context, claiming greater accuracy is a huge part of the experiment. So if you're not using your significant figures correctly, whoever's evaluating your work, whoever you've reported to, whoever you've submitted your lab report to, if you're working for a company, whoever you've submitted your final measurements of the analyte's concentration to, are going to read into the accuracy that you claim in your final result based on the number of significant figures you include in your measurement. So what exactly do we mean by that? Let's say we do an advanced microscopy experiment and we measure the diameter of a single benzene molecule. Let's say we repeat that experiment 10 or 20 times and we come up with an average diameter for a benzene molecule, and the average diameter of the benzene molecule works out, after crunching our data in Excel, to be 0.2947 nanometers. But is that equally good as saying that the benzene molecule is 0.29 nanometers across? Or is there a difference in science between saying the benzene molecule is 0.29 nanometers across or 0.2947 nanometers across? Well, the key is yes, there is. If you're talking about reporting scientific measurements, the more significant figures you report, the more numbers you include after the decimal place, the greater accuracy in your measurement you're claiming. So for instance, if you report the diameter of the benzene molecule to be 0.29 nanometers, well, that's two significant figures. And what you're saying with that average benzene molecule diameter is that you know the diameter of your benzene molecule, or you can measure the diameter of a benzene molecule with the microscope to 1/100th of a nanometer. So 0.2, that's tenths of a nanometer. 0.09, that's hundredths of a nanometer. So if I report the diameter of this benzene molecule, the average diameter, to 2 sig figs, I'm saying that using my technique, I can measure the diameter of that benzene molecule to 1/100th of a nanometer. And that's what my microscope can reliably show me. If I say, though, that I can measure the diameter of the benzene molecule to tenths, hundredths, thousandths, 10,000ths, if I can measure it to a 10,000th of a nanometer, I'm saying that the microscope, that the technique I used, is a lot more accurate than if I report the number to 2 sig figs. Now later in class, we'll show you how you can use statistics and how you can use fundamental information from the instrument to decide whether you can reliably report a measurement through a microscope to 2 sig figs like this or 4 sig figs like that. But all I want you to recognize right now is that the more significant figures you include in your measurement, the greater the accuracy you're claiming. The first skill we want to brush up on, when you see a number or when you read a number in a scientific context, that you can instantly and immediately and accurately identify how many significant figures are in the measurement. And there's a couple of rules that you've been exposed to before in general chemistry for identifying whether digits reported in a measurement, numbers reported in a measurement, are significant, whether they're not significant, or whether they just might be significant. And as a reminder, the first rule in this process is that any number that's reported in a measurement that's not a zero, any digit that's not a zero, is a significant number. So if you're trying to decide how many significant figures there are in a measurement, you're only really trying to decide whether the zeros in the number are significant or not significant, because any non-zero number reported is significant. Zeros are where you have some ambiguity, and that's where you have to use the rules to decide. So I consider kind of rule zero in this process is if you see a measurement, any non-zero numbers expressed in the measurement are considered significant figures. And they tell you something about the accuracy of the measurement. You have to make decisions about the zeros. So rule number one, if you're reading a measurement and you see a zero in the middle of a number, that's like any other digit. A zero in the middle of a number is a significant figure and is part of the statement of accuracy that comes along with the measurement. So for instance, if you measured out 205 mils, we know the 2 and the 5 are significant figures. Because the 0 is in between the 2 and the 5, we know that this 0 is also significant, and therefore a measurement of 205 mils has 3 significant figures. Now, in contrast, zeros located at the beginning of a number are not significant. They're only there to help you locate the decimal point. So what do we mean by zeros at the beginning of a number? So for instance, if you measure out a reagent on the analytical balance and the mass of the reagent is 0.2056 grams, we have to apply our rules again to figure out how many significant figures there are in the measurement. And all the non-zero digits are significant, so the 2, the 5, and the 6 are significant figures. This 0 is in between the 2 and the 5, so this 0 is a significant figure. The 0 we have to make a decision about is the first 0, 0.2056. The first 0 is not significant in this case because all it's doing is helping you locate the decimal place. It's saying, hey, heads up, we're making it a little more obvious that the decimal point is here right before the 2. This 0 has nothing to do with the accuracy of your measurement. It's just telling you where the decimal place is. A good test for this is writing measurements in scientific notation, although a little more old-fashioned in a lot of cases now, really helps you to decide whether numbers are significant or not significant. If we were to write this number in scientific notation, this would be 2.056 times 10 to the negative first grams. And this 0 would not be part of the number in scientific notation. Therefore, this 0 that precedes the decimal point is not a significant figure. It's just helping us show where the decimal point is in the number. So 0.2056 grams, there's 4 sig figs in that measurement. Zeros at the end of the number, but after the decimal point, are always significant. So any zero that comes at the end of a number and after the decimal point, has to fulfill both those criteria, is always significant. So for instance, if you reported the diameter of a molecule as 5.0 nanometers, then the 5 is significant because it's a non-zero number. The decimal point is here, and the 0 after the decimal point ends the number. Therefore, this 5.0 has 2 sig figs. This 0 is significant. Rule number 4, zeros at the end of the number and before the decimal point may or may not be significant. It's not clear based on the reporting convention. So if you see zeros ending a number but there is no decimal point, then you have a decision to make based on what you know about the measurement as to how many significant figures there likely are in the measurement, but you can't say for sure. So for instance, if I told you something weighed 5,000 grams, it's not clear under the rules how many of these zeros are significant figures. We know for sure that the 5 is a significant figure, but without writing this number in scientific notation or including the decimal point, we don't know how many significant figures there are. It could be just the 5 is significant, so there's only 1 sig fig. More likely, at least the 5 and this 0 are significant figs, but we don't know for sure. So a measurement like 5,000 grams, not written in scientific notation, and with no decimal point, could have 1, 2, 3, or 4 significant figures. Lastly, certain numbers are exact. And what we mean by exact in a scientific context is if I can count something with no actual margin for error about whether I can count it or not. Like I can count number of people in a classroom, or I can count number of dollar bills in my wallet. Those are exact numbers. Or if there's a number like, by definition, there are 365 days in a year. Not actually true because of leap years and conventions like that. But if we can say that there are 365 days in a year, or we can say there's 12 eggs in a dozen, those measurements have infinite numbers of sig figs because we could carry out zeros as far as we wanted past the decimal point. It's an exact number. So if I count people in class and I say, well, there's 4 people in class today, hopefully there's more than that. But if there's 4 people in class today, then I know there's exactly 4. I don't have any trouble deciding whether there is or is not 5 people or 3 people. I know there's exactly 4 people. So when you are dealing with counting numbers, the rules for significant figures don't apply in the same way. Significant figures only apply to scientific measurements where we're trying to make a measurement on something and we're trying to determine the length or a property. If we're just counting numbers, counted numbers, or numbers that are used to define something by definition, like Avogadro's number, are considered to have an infinite number of sig figs. So I think most of you guys will probably get back to the point where you can identify the number of significant figures that are reported in a measurement pretty quickly. The last thing we want to do with significant figures is give you a little reminder about when you do a calculation, how many significant figures should you report in your answer. And the practice problems that follow this module will give you a little more practice and a little more review in this skill. Again, this is something I think you guys will broadly remember, but do refresh these rules because you can forget little things here and there. Lastly, a disclaimer. When we talk about how many significant figures should be included when answering a problem in class, which is based on a single measurement, those rules are not the same rules for significant figures that govern your work in the lab. So as the term goes on and as you get deeper into your lab curriculum, you will review how to use statistics to determine the right number of significant figures to report when you did an experiment. These are just rules we'll use when we're solving word problems in class, when we're usually answering something based on a single measurement, not a set of measurements. Okay, so remember when you're doing a calculation, the right number of sig figs is always reconciled at the end. As you're going through a calculation, you don't round down to a set number of sig figs after each step in your calculation process because that introduces rounding error. When you're working a problem in class, have your calculator carry all the numbers that are available as a result of the answer, and then when you're done with your calculation at the very end, when you're about to report your answer, consider these rules, which are based on the mathematical steps you did, to determine how many sig figs to report in your final answer. Okay, so if you are doing a word problem that involves multiplication and division, the key thing to remember is that as a result of a multiplication or division step, the answer can't have more significant figures than any of the original measurements. In fact, the answer should be reported with the same number of significant figures as the measurement that you used in the calculation with the least number of sig figs. So if you're doing a multiplication and division step like density, and you have 2 significant figures in the mass and 3 significant figures in the volume, well, density is mass divided by volume, and therefore your answer should have 2 sig figs, no more, because your mass only had 2 sig figs. Addition and subtraction steps are a little more complicated. They run by different rules. And the idea is that if you do an addition and subtraction step, the correct number of significant figures to report in your measurement is that your answer can't have more digits to the right, can't have more decimal places. The answer can't have more digits to the right of the decimal point, can't have more decimal places than any of the original measurements. And when you report your number with correct significant figures after an addition or a subtraction step, you should truncate your answer so that the number of decimal places you're reporting matches the number that has the fewest numbers after the decimal point. The hard part about these rules is when you're doing your calculations and you're performing multiple steps, remember that you do all your calculations and you don't worry about significant figures till the end. Once you've solved the problem, you look back at all the mathematical steps that you did, and then based on the steps you did, and whichever step would show you entitled to the fewest number of significant figures, that's how many significant figures you report in your answer. We won't do an example with that just yet. We're going to save some of this significant figure talk until the end of the next module where we actually solve a problem using dimensional analysis, and then we'll go through and review with you a little bit more about how we're thinking about the significant figures and how we arrive at our final number of significant figures at the end of the calculation. But hopefully this has been broadly reviewed for some of you. It's okay for stuff you've had in previous classes to have driven some of these original rules out. Significant figures often seem just a little bit pedantic when you're first exposed to science. But one thing you need to remember is that in analytical chemistry or any experiment-based science, significant figures that you report in your measurement are telling other scientists how much accuracy you're claiming in your measurement. And obviously you need to claim an accuracy in your measurement that goes along with the experiment you did, no more, no less. So significant figures are extremely important. Review very heavily identifying the number of significant figures in any given measurement. We'll talk more about how we decide how many significant figures we're reporting at the end of a calculation in class when we do the dimensional analysis example in the next module. Go ahead and try the practice problems that follow this if you need a little more review, and feel free to ask me any questions if you feel that I've explained something in such a way that causes you to doubt how you're already doing it, or whether it's raised any questions that where you think, maybe I don't remember that as well as I thought it did. Regardless, I'll see you in the next module.